begin with my overview. I'm going to cover my background, two different algorithms. One of which I studied was ITRLP, and the second one listed up there is the one that I actually modified the ITRLP and named it ITRLP2. I'm going to cover my goals, experiments and results, conclusions, contributions, and future work. To begin with divisible load theory, it is an established mathematical framework used for studying divisible load scheduling. It also uses a linear continuous model for loads to be partitioned for parallel processing. Some real-world applications for divisible load theory include dataset, signal, and image processing, database searching, and matrix computations. You can think of a divisible load as basically a task that can be split up into a set of subtasks. And you take those subtasks and then give them out to a set of workers to complete. And the whole idea behind that is to reduce the total amount of time required to complete the task. But rather than thinking of it in terms of subtasks and workers, we're going to think about it in terms of load fractions and computer processors. So you'll see here we have on the outside, those are worker processors, and in the very center is a master processor, P0. And this is a heterogeneous star network. And the processors on the outside are varying in size. What that represents is how powerful the processor is. The larger it is, the more powerful. And the same goes for the network links. The thicker the link, the more data can pass through it. Now there's one problem with this star network. You'll notice that the distance between the master processor and all the worker processors is the same. And that's basically a simplification that the makers of the ITRLP algorithm assumed. But I think realistically that it should be assumed that there is varying distance between the master and the worker processors. And what that distance represents is what is called latency. And latency is basically the time it takes to initiate a connection between two processors. So this is definitely a more heterogeneous star network, in my opinion. So when dealing with varying levels of heterogeneity, communication plays a very important factor, and load should not just be allocated to any given processor. So the question is, what is a good schedule for load to achieve optimal time? And the answer is, it depends on the system parameters. And they are as follows. We have communication C, which is basically the bandwidth cost on each network link. Then latency is the delay on each network link. And communication E is how much processing power it takes on that processor, on each processor. So along with those parameters, we have three phases, and they are as follows. We have allocation, and what that is the master processor allocates load fractions to its worker processors. Then for the computation phase, we have worker processors computing their load fractions into results. And the collection phase is where worker processors have finished computing and they send the results back to the master. Oh, one thing I forgot to mention about the heterogeneous star network that ITRLP uses, it doesn't actually use latency at all in its functionality. So it would assume that latency is 0, which would mean that all of your processors are pretty much connected. So I'm going to show you a simple example with three processors now. We have two new variables involved here. Sigma A represents the allocation order, and sigma C represents the collection order. So now this is a Gantt chart, and we have our three processors there, and you can see the time passing by. And we have our three phases. The first phase in red is allocation. Green is our computation, and the blue is the collection phase. And you'll notice here that in both the allocation and collection, that none of the communications overlap. And what this is a simplification that I've made because of what is called the single port model. And this is what the ITRLP actually assumes. So just to keep it simpler, it is assumed that a master processor can only communicate with one worker processor at a time. But that doesn't mean that the worker processors can't compute at the same time. So you'll see there that by the time the third one is allocated, all three processors are actually working at the same time. And we have a few distances there. The y distance represents the idle time between the last processor allocating and the first one that actually sends results back. And then our x distances represent the idle time between when a computation finishes on a processor to when it actually sends results back. So now I'm going to show you this linear cost function which the ITRLP uses. And what it measures is the time units that are involved for the allocation phase and the computation and the collection phases for one given processor. And you'll also notice that we have two new variables. The delta is the result factor. And say we had a result factor of 0.5. That means that our result set is going to be half the size in data than what was originally allocated. And the other variable is alpha, and what that is our load fraction. And you'll notice it's multiplied against all of our parameters that are used in this linear cost function to make it linear. But there's one parameter that's missing there, and what it is our latency cost. So what we need to do is add this fixed cost and convert our linear cost function to an affine cost function, which is essentially linear just with that fixed cost added in. And you'll notice that it's pretty much the same, but we have our latency added into our allocation and collection. And the reason why we have to add it in twice is that we have to initiate a connection for the allocation phase, and then we also have to reinitiate the connection for the collection phase. So what the divisible load scheduling algorithms that I've studied use what is known as a linear program solver. And what is up on the board here, I'm not going to explain it too much in detail, but it is a minimization problem that minimizes the time taken to compute a divisible load. So you'll see up here that constraint 1, on the left-hand side, it is the lower bound for the time it takes for the total time spent in transmission of load to all processors that must receive load before a processor K can start computing its load. And then it also has the computation time for processor K itself and the time for processor K and all of its subsequent result transfers. And that constraint is actually used for however many processors you have in your system. So if you have 5 processors, you have 5 constraints. 5 copies of that, just running it for each processor. Now, constraint 2, what it does is it enforces the single port model that I was talking about. And on the left-hand side, it represents the lower bound for all allocation and collection transmissions for all the processors. Now, constraint 3, it ensures that the entire load is distributed throughout any number of the processors, maybe not all of them. And constraint 4 is the non-negativity of our decision variables.